Well, hello everyone. It's Wednesday, so it's time for our live stream. Thank you to my moderator for getting everything set up. So, as you can tell from the title in the upper left hand part of the screen here, we are going to work with empirical and molecular formulas. So, we're going to do really two types of problems. The first type, I find the easier type, is where you start with some kind of percent composition, and then from that you derive the empirical and then possibly the molecular formula. And then the last problems that we're going to do, I find to be a little bit more difficult, few more steps, it's just a little bit more involved. And that's where you're going to take a combustion analysis or an analysis of the compound. And then from that, you are going to derive empirical and molecular formulas. But as always, I like to start with the easier problems first and then kind of work up to the more difficult problems. All right, so let's go ahead and get started with our first problem. All right, so again, this is a percent composition problem. And maybe before we jump into this problem, let me just do a very quick refresher on the difference between an empirical and a molecular formula. So an empirical formula is the lowest ratio of the atoms in the compound. So let's look, for example, I think a great example of this is actually benzene. So we know that benzene actually has 6 carbons and 6 hydrogens. So this is its molecular formula. The molecular formula shows exactly how many, say, carbon atoms and hydrogen atoms are in benzene. But the empirical formula for benzene is where you take that ratio of atoms and you reduce it as much as possible. So right now we have 6 carbons and 6 hydrogen. That ratio, 6 to 6, can actually be reduced down to just CH, or 1 to 1. So this would be benzene's empirical formula. Now, sometimes the molecular formula is the empirical formula, and sometimes they are different. So this is kind of at the end of the problem. If we are given a molar mass, that is where we will determine if the molecular and empirical formulas are the same, or if we need a multiplier to go from the empirical formula to the molecular formula. Okay, so I just wanted to kind of lay that foundation there. Let's start on this actual problem here. This is not, we're not doing anything with benzene. Actually, what I will do is I'll just erase this so it doesn't cause any confusion. That was just my off-the-cuff example there. All right, so we have an unknown compound. We know that it is 56.79% carbon, 6.56% hydrogen, and 28.37 oxygen, and 8.28% nitrogen. So what we want to know is just the empirical formula of this unknown compound. All right, so what we are going to do is, you can assume anything, but I find it's easiest to assume you have 100 grams of this compound. Because if you have 100 grams of this unknown compound, it means that you have the 56.79 grams of carbon in this compound, and you have 6.56 grams of hydrogen. So again, you can assume you have any amount of the compound, but I find that assuming you've got 100 grams of the compound just takes those percentages right to decimals and makes it easy. So assuming we have 100 grams, let's just write this down. So if we've got 100 grams of this unknown compound, we have 56.79 grams of carbon. We have 6.56 grams of hydrogen, 28.37 grams of oxygen, and 8.28 grams of nitrogen. Let me just make that decimal a little bit bigger. All right. So our next step, after assuming we have 100 grams of this unknown compound, is to take each of these grams of our different elements and convert it into moles using the molar mass. So for carbon, I am simply going to take this and I'm going to multiply it by the molar mass of carbon, which of course is 12.0107. Although, frankly, in terms of these problems, having a lot of decimal places in the molar mass really isn't going to change much of anything. Okay, let's just do this for all of these, and then I'll write down kind of what these answers are. So for hydrogen, we're going to multiply by the molar mass of hydrogen. So that is 1.00794. We're going to do the same thing for oxygen. I have made these a little bit too close together. I am sorry. 0.9994 grams of oxygen. And you know what? This is just kind of driving me crazy. I'm going to bump nitrogen down just a little bit here. All right, so I'm going to rewrite nitrogen. Let's see. Nitrogen was 8.28 grams of nitrogen. And again, I am just multiplying by the molar mass of nitrogen. 0.0067 grams of nitrogen. And of course, I'll show this in different color. You want to make sure that you put these conversion factors in the right place. So my grams of carbon cancels out. So I'm left with moles of carbon, and the same with the hydrogen and the oxygen and the nitrogen. Again, when you're doing these conversions, it's really easy to accidentally flip-flop these conversion factors. Okay, let's get some numbers in. So for our carbon, if we do this math, we get 4.7283, and now this is moles of carbon. So for hydrogen, again, just going ahead and converting it to moles. Obviously, it is nearly the same thing. So that's moles of hydrogen. And our oxygen here gives us 1.7732 moles of oxygen. And our nitrogen is 0.5911 moles of nitrogen. Okay, so we have taken our grams and we have simply converted it to moles. The next thing we want to do is we want to figure out the ratio of all of these atoms. So of course, the great thing about having moles is, remember, moles is tied to the number of atoms you have. It's usually such a large number of atoms that it's easier to deal with moles. So to find this ratio, what I'm going to do is I am going to look at all my different moles. I'm going to pick the smallest number, and I'm going to divide all of my other numbers by that smallest number. I'm going to actually change color here. So my smallest number is going to be my moles of nitrogen, and that is 0.5911. So that means I'm dividing all of these moles by my moles of nitrogen. So I'm dividing this one and my oxygen and my hydrogen. I'm sorry, I really should have left myself more space because we're still getting crunched here. Okay, so now when I do this calculation, what I get is this moles of carbon becomes 7.999, which is 8. Again, we're looking for our closest whole number here. So it doesn't matter that that is 7.999. You can assume that is 8. So these numbers don't always come out completely exact. You might have, like this one was just under 8, or you might have 8.011. That's still 8. So for hydrogen, when we do this, we're going to get 11.01. Again, you just assume that that is 11. You're looking for the closest whole number. And for oxygen, that ends up actually being, again, 2.999, which we can assume is 3. And of course, our nitrogen gives us 1 exactly. So this gives us our empirical formula. It gives us the ratio of all of the atoms. So if I'm writing the empirical formula for this unknown compound, I'm going to write C8H11O3, and then just N for nitrogen. So again, this is why we go for the closest whole number. You would never see a molecular formula or an empirical formula that says carbon 7.999, right? We always work with whole numbers here. So you want to, again, look for that closest whole number. All right. Any questions? No questions? Let's go ahead and go to our next one. Okay, so now we've got another unknown compound. These are all going to be unknown compounds. This is generally what we do when we have a compound is, especially if you've synthesized a new compound in lab, you try to figure out what the molecular formula is. Okay, so this time, this unknown compound, we know it consists of carbon, hydrogen, and oxygen. We have 41.39% carbon and 3.47% hydrogen. This time we are given a molar mass, so we know the molar mass of this unknown compound, and we want to get to the molecular formula. So in our previous exercise, we only needed the empirical formula, but in this one, we are going to need to find the molecular formula. And again, we don't know, those may be the same or they may be different. But just like we did before, we're going to assume we have 100 grams of this. Now, we have a little bit of a twist here that we're going to have to deal with before we assume our 100 grams. So we know that this compound consists of carbon, hydrogen, and oxygen, but we're only given the percentages for carbon and for hydrogen. So we need to determine our percent oxygen. Now, this is actually very easy, but it's a step that is often missed. So make sure you have percentages for all of your compounds. So we need to get the percent oxygen, and this is simply going to be 100% minus these 2%. So all of your percentages, if you add them up, should give you 100%. So we will add our 41.39% for carbon plus our 3.47% of hydrogen. Again, subtract that from 100%, and that will tell us what percentage is oxygen. And this is a very, very common thing that a lot of problems won't give you the final percentage of whatever your last element is, and you just have to subtract from 100. Okay, so if we do this really quick math, we figure out that oxygen is 55.14%. All right, now we can assume that we have 100 grams of this compound. So we have 41.39 grams of carbon. I'm going to give myself more space this time. 3.47 grams of hydrogen. And of course, we just figured out the oxygen. That is 55.14 grams of oxygen. So just like before, we want to take these grams and convert it into moles. So we're still just doing, just like last time, the molar mass. So we're going to do the molar mass of carbon, 0.107, the molar mass of hydrogen, 794. Okay, and then, of course, convert finally this oxygen using the molar mass of oxygen. 994 grams of oxygen. Oops, so I left off my units there. Okay. So if you plug this into your calculator, you are going to get 3.446 moles of carbon, 3.443 moles of hydrogen, and 3.446 moles of oxygen. Okay, so you can already see that this is a pretty nice ratio here. All right, so we're going to take our smallest number, which in this case is going to be our hydrogen, and we're going to divide everything by it. And divide this by our moles of hydrogen. And you can already see that we're going to get ones for all of this. Oops, let me switch back to blue. So this is 1, 1, and 1. So you're right. Carbon and oxygen are not exactly 1, but again, we're looking for that closest whole number, and 1 is definitely it. So if I'm going to write my empirical formula for this, I have 1 carbon, 1 hydrogen, 1 oxygen. So my empirical formula is simply CHO. But my problem asked me for my molecular formula, and it gave me one extra piece of information. It told me the molar mass of my compound is 116.07. Well, let's first find the molar mass of my empirical formula, and that is 29.018 grams per mole. So clearly my empirical and my molecular formulas do not match up, and I need to figure out what the ratio is between them. Again, we're looking for a whole number here. There are really 2 different methods that I've seen students use. You can do a guess and test. You can say, well, maybe it's times 2, and you could take your empirical formula, you can multiply it by 2 and see if you get your molecular formula. What I like to do is I actually like to calculate the ratio, especially if it doesn't immediately jump out to me. So I will take the molar mass of the molecular formula. So I'll call that the molecular mass, and I'll take it over the empirical mass. And that should give me the ratio between the empirical and the molecular formula. Again, I'm looking for a whole number here. So my molar mass for my molecular formula is, of course, given to me. That's 116.07 grams per mole. And I just calculated the molar mass for the empirical formula, and that is 29.018 grams per mole. And this gives me a whole number of about 4. It's actually like 3.99, but again, we're looking for whole numbers. So my ratio is 4, which means my original CHO is going to go to C4H4. 4. You can also, if you want, if you know the ratio, you can also just take your whole numbers here and multiply by the ratio, and that will also tell you how many of each atom you have. Now, this one was really easy because they were all 1, but sometimes in the more complex ones, it makes sense to put that there. Either way, whichever way makes the most sense to you. All right, any questions? All right. No questions? Let's go ahead and go to our next problem. All right, so this time we have, again, another unknown compound, and it is made up of scandium and oxygen. So we are given our percentages of scandium and our percentages of oxygen, and we just want to know the empirical formula. So we don't need to mess with doing the molecular formula. We just want empirical formula. We just want the lowest whole number ratio. Okay, so again, just like always, we're going to assume we have 100 grams of this compound. So that will give me 65.2 grams of scandium and 34.8 grams of oxygen. My next step is to convert grams into moles. So I'm going to use the molar mass of scandium, and that is 44.9559. And of course, for my oxygen, that is going to be about 16. Okay, let's do these calculations. So converting my grams of scandium into moles of scandium, I'm going to get 1.45 moles of scandium, and for oxygen I'm going to get 2.1 grams. Sorry, that is not grams, that is moles of oxygen. So again, now that I've converted into moles, I'm going to divide by my smallest number, which is my moles of scandium. Let me just change that into green. So this goes 1.45 divided by 1.45. All right, now to find my ratio. Of course, scandium is easy, it's just 1. But if I do this for oxygen, I end up at about 1.5 1.5. Now, this is a problem because we're looking for our whole number ratios. Well, 1.5 is right in the middle of everything. So what do? Do you round up to 2? Do you round down to 1? You actually do something entirely different. So 1.5, if I were to write that as an improper fraction, that is 3/2. And of course, I can't, well, I could, but you can see it doesn't quite work. So I could write scandium, oxygen, 3/2, but you can look at that and say, no, that's not right. That is not your lowest whole number ratio. So how do we deal with this fraction in here? How do we deal with this half? Well, we multiply by 2. So if I'm going to take this 1.5 and multiply by 2, and of course that is going to give me 3. Now I have to also do that to scandium, so that also gets multiplied by 2. And now instead of having that monstrosity, you have scandium 2O3. And that is the empirical formula. So you will run into certain empirical formulas as you're doing this. You might see 0.5s, especially anywhere. This one was 1.5. You might have a 0.5. You might have a 2.5. Just recognize that as a half. And so to get rid of that 2 in the denominator, you're going to need to multiply by 2, and then you will end up with a nice, beautiful whole number ratios there. So this looked like a really simple problem, but it had a very interesting twist to it. Okay, any questions? All right, no questions? Then let's move on to our next one. Okay, aspartame. We're given a molar mass of 294.3. It's composed of carbon, hydrogen, nitrogen, and oxygen. So we want to determine its molecular formula, and that makes sense because we have a molar mass. And we are given the following data. Okay, so we have 57.14% carbon, 6.16% hydrogen, and 9.52% nitrogen. Now, as usual, we need to calculate our final percentage, and that is going to be our final percentage for oxygen. All right, so let's go ahead and do that first. So our percent oxygen here is just going to be 100% minus the sum of all of our others. So this is 57.14% plus 6.16%, and our nitrogen last. All right, so this will give us our percent oxygen, and if we do this, we get 27.18% oxygen. Okay, great. Now we have all of our percentages. So just like we've done with all of our other problems, hopefully you're seeing a pattern here. We're going to assume that we have 100 grams of this compound. So we have got, I'm going to try to make sure I give myself enough space here. Here is our carbon and our oxygen, our hydrogen. Our nitrogen, 5.2 grams, and last but not least, our 27.18 grams of oxygen. All right, so let's take each of these grams and let's convert to moles. Okay, so here is carbon. That is moles of carbon, hydrogen. Here is our molar mass of hydrogen. Nitrogen is going to be about 14. Oops. Almost wrote hydrogen there. Okay, and last but not least, let's get oxygen in. 994. Okay, now I know all the calculations that I want to do, so let's actually do these calculations. So my moles of carbon are going to be 4.76. This is going to be 6.10. Nitrogen is 0.68. And oxygen, we get 1.70. All right, so now that I've converted everything into moles, I want to divide all of my moles by my smallest number, which in this case is going to be my nitrogen. So let me switch colors here. So that is going to be divided by 0.68 all around. Okay, so now let's figure out what hopefully my whole numbers are. Okay, so carbon, when you do this, you see it comes to about 7, so that's great. Hydrogen ends up being 9. Of course, nitrogen is 1. And of course, when we do oxygen, we've done well so far with our whole numbers, but oxygen ends up being 2.5 again. All right, so we have another half, which means everything needs to be multiplied by 2. So we're going to multiply by 2 all around. All right, so this is going to give us 14 carbon and 18 hydrogen and 2 nitrogen and 5 oxygen. So right now my empirical formula is C14 H18 N2O5. All right, so this is my empirical formula, but of course I want to determine the molecular formula. So let's first just calculate the molar mass of my empirical formula. So if I do that, what I find is I actually get 294.3, which is matching with my molar mass up here. This means my empirical formula is my molecular formula. So that is my molecular formula for aspartame. Okay, any questions? Nope, no questions. It looks like we are ready to move on. All right, so here we're going to start with our, taking it up to the next level, our more difficult problem. So this is a combustion analysis problem. So what we've got is we've got an unknown compound here. Let me switch. And it contains carbon, hydrogen, and nitrogen. So what we have done here is we've taken a small sample and we have undergone combustion analysis. So we have formed this much carbon dioxide, excuse me, and this many grams of water. All right, and we know the molar mass, so we're going to determine molecular formula. All this we're going to deal with that at the end of the problem. So let's just focus on our sample and what has formed here. Now, what we assume is that all of the carbon in this unknown sample has gone to form carbon dioxide. So we assume that we haven't left any carbon in this little sample of our unknown compound. We also assume that all of our hydrogen has been converted into water. So these are really important assumptions here because we are going to use them to determine the amount of carbon and hydrogen. Now, once we know our percentage of carbon and hydrogen, then we can determine nitrogen again just by subtracting that from 100%. But let's focus in on our carbon and our hydrogen first. All right, so what we're going to do here is we're going to take our amount of, we're going to start with our amount of carbon dioxide. So that is 0.1638 grams of CO2. And what I want to do is I want to take that grams of carbon dioxide and convert it into grams of carbon. So how many grams of carbon per gram of carbon dioxide? I'm going to have 12.011 grams of carbon per 44.009 grams of carbon dioxide. All right, so it's pretty obvious that my 12.011, that's just my molar mass of carbon. My 44.009, that is actually the molar mass of carbon dioxide. So what this does for me is this converts my grams of carbon dioxide into grams of carbon. So this means that I actually had 0.4470 grams of carbon in my sample. Now, once I've determined the grams of carbon in my original sample, now I want to calculate the percent carbon. So I take this 0.04470 and I am going to divide by the mass of my total sample. So this is the mass I started with, the 0.1156. This is my grams of sample. And what this will do, times 100%, is will give me my percent carbon in my original sample. All right, so if you do this calculation, we get 38.67% carbon. Now, that puts us right where we were with our easier problems when we started with percent composition. So I'm going to kind of finish with carbon right now. Let's go ahead and do the same thing for our hydrogen, which again we assume was all converted into water. So I am starting with my mass of water formed, which is this number right here. So this is grams of water. And just like before, I'm going to convert this into grams of hydrogen. Now this is a little bit tricky. So I'm going to put my molar mass of water in the denominator. But because water is H2O, it's not simply the molar mass of hydrogen, the 1.008. Because there are 2 hydrogen atoms, this mass in the numerator is 0.016 grams of water. So that is why that is a 2, because water is H2O, which adds, again, just a little bit of a trick. So my grams of water cancel, and I'm left with grams of hydrogen. Okay, so if I do this calculation, what I get is 0.01876 grams of hydrogen. Now that I know the grams of hydrogen in my original sample, I want to get, again, the percent hydrogen, just like I did for the carbon. So I am dividing by my grams of my original sample that I analyzed, and I'm going to multiply by 100%. And this gives me a percent of 16.23%. Okay, so I've taken my numbers for my combustion analysis and I have converted them into a percent. The last thing before we assume we've got 100 grams of this compound and go through kind of our normal routine is we've got to calculate the percent nitrogen. So our percent nitrogen here is simply going to be, again, the difference from 100. So here is my percent carbon and my percent hydrogen. And that gives me about a 45% nitrogen. All right, now I've got all of my percents. So this problem becomes just like all of the previous problems that we've done. So we're going to assume that we have 100% of everything. And I'm kind of thinking that I'm going to put this on another page because I'm running out of space here. So let's add in another page. And we'll come right here. All right, and we can always go back and get other data. But we had 38.67% carbon. So again, assuming 100 grams, that is how many grams of carbon? 16.23% hydrogen. So there are my grams of hydrogen, and nitrogen was 45.10 grams of nitrogen. All right. Now we need to convert these grams into moles. I know that there's a lot of grams and then into moles, and then percent, and then into grams, and then moles. So it's really important not only that you write down your units so you know where you are, but that you keep your work as organized as possible so that, again, you keep track of where you are in the process and what step is next. All right, so let's go ahead and convert these grams into moles. And we'll just do the same thing with all of these, and then I will actually show the calculation here. And last but not least, we'll do nitrogen. Okay, so here is my molar mass of nitrogen. Now I'm going to get all of my moles. So I have, it's going to give me 3.220 moles of carbon and 16.10 moles of hydrogen and 3.220 moles of nitrogen. So now I just need to find my lowest number, which is going to be my 3.22. And let's get our ratio. At least we know that carbon and nitrogen are going to be quite easy. Let me fix that decimal point. Okay. All right, so this is what we get. Oops, let me switch. Obviously, these guys are both 1. That's easy. But if I take my 16 over my 3.22, I get 5. So I don't have to deal with any halves. That's fabulous. This gives me an empirical formula of CH5N. So I have 1 carbon, 1 nitrogen, and 5 hydrogen. And let's take this empirical formula and let's go ahead and calculate our molar mass of our empirical formula. So let's go empirical molar mass is 31.058. And let's go back to our original problem, and we can see that the molar mass of the molecular formula is 93.174. So in this case, our molecular and empirical formula are different. We just need to figure out that ratio. So again, I am simply going to take the molar mass of my molecular formula divided by the molar mass of my empirical formula, and that should tell me my ratio. So again, I'm taking, not empirical first. That would give me the inverse. All right, I'm going to take my molecular molar mass over my empirical. And that is the 93.174. That's again from the previous page. And I just calculated it. If you're ever trying to find this ratio and you end up with a fraction, just double check and see if you need to maybe take the inverse. I have done that many times. Okay, so if I do this division, I get a ratio of a nice whole number of 3, which means that my molecular formula is just 3 times my empirical. So this will be C3H15N3. And there's my molecular formula. This one was definitely a longer problem. These are a little more complex, more steps. Any questions? No questions? Okay, let's go ahead and finish up here. We've got one more problem. Again, this is going to be a more difficult one. Okay, so again, we have an unknown compound. It contains carbon, hydrogen, oxygen, and nitrogen. All right, so we're going to take a 0.15 gram sample, again, undergo combustion analysis. We're forming carbon dioxide just like before and water. All right, so that's going to give us our carbon and our hydrogen. And then we have a different sample. Okay, so that's going to be important. And it's going to form this many grams of ammonia. Okay, so for our second part here, just like we are assuming that all of the carbon goes to CO2 and all of the hydrogen goes to water, we're going to assume that all of our nitrogen is converted into ammonia. So this is going to be treated the same way, but we're going to have to watch and make sure we put the correct numbers in the correct spot because we have 2 different samples here. So we need to make sure we keep this mass of the sample with our CO2 and our water, and we need to make sure that we pair this sample mass with our ammonia to get our nitrogen. And then once we have carbon, hydrogen, and nitrogen, then again, once we've got our percentages, we can figure out our percent of oxygen. And then we'll just save the molar mass until the very, very end, and we'll get our molecular formula. Okay, let's start with our 0.157 gram sample, and let's take care of our carbon dioxide and our water, and then we'll come back to our ammonia. All right, I think I'm definitely going to need another page here because this is going to be a lot of calculation. All right, so starting with our CO2 for our 0.157 gram sample, we have 0.213 grams of carbon dioxide. And just like before, we really want to get to our grams of carbon. So I am going to put my molar mass of carbon dioxide in the denominator and my molar mass of carbon in the numerator. Okay, and that gives me 0.0581 grams of carbon. Now, this grams of carbon, again, we assumed all of it was converted, came from, again, my 0.157 gram sample. So I'm just going to divide that by 157 grams. This was my total sample times 100%. And this will give me my percent carbon. So this gives me 37.01% carbon. Okay, great. That's carbon. Let's go ahead and take care of our water and our hydrogen. So we formed 0.0310 grams of water. And if you remember from the previous problem, I'm going to put my molar mass of water in the denominator. And don't forget, because water is H2O, it's not just your molar mass of hydrogen, but 2 hydrogens there. Grams of hydrogen. All right, so if I do that calculation, I get 0.00347 grams of hydrogen. Again, this was the same sample for my carbon, so this is the mass of the sample that I'm going to use. Grams of sample, and of course times 100%. And this gives me 2.21% hydrogen. Okay, so these are looking pretty good. I next need to do my nitrogen, and that's forming ammonia. All right, again, same treatment, but we just need to make sure we keep our numbers straight. So I formed 0.0230 grams of ammonia. Just like before, I'm going to put my molar mass of ammonia in the denominator. And my molar mass of nitrogen in the numerator. All right, and that gives me 0.0189 grams of nitrogen. Now here's where it's really important to remember that this sample of ammonia came from this separate sample of our unknown compound. So my mass now is 0.013 grams of sample times 100%. And that gives me a percent nitrogen of 18.35%. All right, so our final percentage is just oxygen, and this this one thankfully is our easy one. So percent oxygen is just going to be the difference from 100%. So here's our carbon percentage, our hydrogen percent, and our nitrogen percent. And that gives us 42.43% for oxygen. Okay. This, I think, is really the most difficult part is figuring out how to go from like your grams of carbon dioxide to your percent carbon. Because once we're in our percentages, then we've just got percent composition and we know what to do to get to our molecular formula. But I want to add another page here because I'm running out of space. So we've got our percentages. Let's assume that we've got 100 grams of this compound, and let's get our lowest whole number ratios. So we are going to have 37.01 grams of carbon, 2.21 grams of hydrogen, 18.35 grams of nitrogen, and 42.43 grams of oxygen. All right, let's convert these to moles. 0.11 grams carbon. Okay, that'll give us our moles carbon. And this will give us our moles of hydrogen. Our moles of nitrogen, 1 mole of nitrogen, and finally, let's convert our oxygen. Grams of oxygen and 1 mole of oxygen. All right. Let's get numbers for all of these. All right, so our carbon ends up being about 3 moles. Our hydrogen is 2.19 moles. Our nitrogen is 1.31 moles. And our oxygen is 2.65 moles. Okay, let's get our ratio now. So my smallest number is my 1.31, my nitrogen. So I'm going to divide everything by 1.31. Let's get some ratios here. 0.31 and 1.31. All right, so when we do carbon, we run into a bit of a problem. I'm just going to go ahead and write it down. We get 2.3. Let's just keep going. For hydrogen, again, we're getting something a little unusual. We're getting 1.6. At least nitrogen is 1. We know that, right? And our oxygen ends up being 2. Okay, so we have seen where we have 0.5, and that's a half, and that's how we deal with anything that is 0.5. But now we've got a 0.3 and a 0.6. Well, if you have done a lot of conversions from fractions to decimal, hopefully you recognize that 0.3 is actually 1/3 and 0.6 is 2/3. So we have both our carbon and our hydrogen. If you turned it into an improper fraction, it would be thirds. So just like to get rid of the halves, we multiplied by 2. To get rid of the thirds, we are going to multiply by 3. I am going to put this in a different color. All right, so everything, of course, gets multiplied by 3. And that is going to give me my lowest whole number ratio. The whole number is key here. That will give me 5, of course, gives me 3, and this gives me 6. So now I have my ratio for my empirical formula. So this is less common than the halves. I feel like having a 0.5 you see pretty often, but less common, but it obviously is there, is when you have either a 0.3 or a 0.6, and that means you've got a third. So you're going to have to multiply that one by 3. But you should end up with whole numbers. Again, these have to be whole number ratios. Okay, so let me switch back to blue. So our empirical formula here is C7H5N3O6, which is pretty big. So I'm thinking that this is probably going to match in terms of empirical molecular formula, but we need to check. So if I take my empirical formula and I calculate my molar mass, so my empirical molar mass is going to be 227.1 grams per mole. Sorry, I have to squeeze that in a little bit. So let's go back to our problem and see. Okay, so you can see here, our molar mass of our compound is the exact same thing. So thankfully we don't have any more multipliers, right? So our empirical formula is our molecular formula in this case, which is good because this is already a pretty big molecule there. Okay, before we end, it doesn't look like there are any questions. I hope you guys found these problems helpful to do. I know that we're coming up into exam season if you haven't already taken your exams. So please feel free to contact me if you need extra help. I do offer tutoring services. And as always, let me know in either comments on YouTube or you can comment on our Facebook page and let me know what else you guys would like to see. Thanks so much for joining us. Bye.